any nice pure colors in here? I don't see. Well, the Time on the Time magazine cover back there. That's a nice red. When I see red, as compared to the blue of the screen below it there, red and blue and the various pure colors like that, what is it that makes light a certain color? It's wavelength and wavelength only. Light is an electromagnetic wave, so if I was to draw a wave form, maybe this is the magnetic field, something like that. Here's the neutral undisturbed wavelength lambda, measured most conveniently from wave crest to wave crest, typifies that particular wave. And the only difference in color is wavelength. So the longest wavelength that we can see is about 7,000 angstrom units. And the shortest wavelength that we can see, violet, is about half of that, about 3,000 or 3,500, let's say 3,500 angstrom units. It really depends on which human eye we're talking about. Violet is one that really is hard to find the exact end of it. So obviously there are wavelengths much longer than red and much shorter than violet. So when we talk about radiation, we're talking about all forms of radiation, not just this narrow band that we can see. And I bet you know the numbers, or the names rather. If I have wavelengths, let's say I have a wavelength lambda, which is only 1,000 angstrom units, well beyond what anybody can see. It's not called violet, it's called what?
Ultraviolet.
That's UV, ultraviolet, of course, UV. There's shorter wavelengths still. If you had a wavelength of, say, maybe 100 angstrom units, that is actually beyond the region that we call ultraviolet. Do you know the name of the next band? Those are X-rays. And then you can have them that are very, very short, like, for example, lambda equals maybe 10 angstrom units, and that's gamma rays. What about the other direction? How about longer? What if we have 10,000, way beyond red? IR, infrared, yes. And I don't really have room to write the rest of them, but if we get longer wavelengths still, they become microwaves. Longer wavelengths still, we call them short wave radio. Longer than that is long wave radio. So there's this huge spectrum of electromagnetic radiation. And for now, when we're talking about electromagnetic radiation, I will call it light. But notice I won't use the term visible light. When I say visible light, I only mean this band here. When I say light, I mean the entire electromagnetic spectrum, ranging from really, really short gamma rays to really, really long radio waves and everything in between. Okay, so, yeah, that's right. And how many colors are there, by the way? Red is one extreme, violet is the other extreme, and in science, I'm not talking your art class. In art class, they have a lot of weird colors, don't they? What in the world is mauve? Or magenta. But in science class, we have how many, do you know? 7. 7. And does anybody remember the technique to recall those 7? That's it. Oh man, you all know it. Your old buddy. You went to school with Roy G. Biv. Red, orange, yellow, green, blue. This was the color of the slot machine, right? And violet. Those are the 7 colors as we define them in science class. And they're always in this order or the reverse order like that. Roy G. Biv backwards. Yes?
What about this RGB combinations?
Say again?
What about this RGB combinations? Like which we blue?
That is,
More.
in my humble opinion, that is a system that's designed to make telescopes easy to use and to estimate the brightest specific color. Estimate. Okay. Scientific technique. We'll get into that in just a few minutes, actually. So fine, that's radiation, and we're going to be talking about electromagnetic radiation. We're talking about everything in the entire spectrum. Now, what is light? The light striking the board comes at my eye and I see white. How do you describe white? It's not Roy G. Biv. It's all of Roy G. Biv, isn't it? And this is key, in equal amounts. If you have equal amounts of all 7 colors, it comes out white. And now it kind of explains why things are the colors that we see. Let's go back to the red of the Time on Time magazine. The light in the room, the light is being emitted as white light. It strikes that paper. There are pigments in the ink that absorb everything except the red. Only the red is reflected back. That's why it appears red. The white surface here appears white because all the light that hits it is reflected, all of it, so it comes back at it white. What is black?
All colors absorbed.
Actually, I like to say black is a behavior, it's not a color. White is a mixture of all colors, and black, this is really important, write it down. A surface is said to be black if. Are you ready? Here it comes. A surface is said to be black if it absorbs all the radiation that falls on it. One more time. A surface is said to be black if it absorbs all the radiation that falls on it. So now, of course, you can begin to understand why this surface looks the way it does. The white light strikes it, all of the white light is absorbed, nothing is reflected back to your eyes that you can see. So we call that black, but it honestly is not. It is not black, because it may absorb all the visible spectrum, but remember, the visible spectrum is a very small band. It will reflect something. That reflects something. It doesn't absorb something. So it's not really black. So the traditional idea that you and I have about black doesn't really apply. The colloquial idea does not apply. Keep in mind that for us, a surface is said to be black because it absorbs all the radiation that falls on it. That includes everything. From the longest radio to the shortest gamma and everything in between. Very, very few surfaces are actually black. And I'd like to turn our attention to what we call black body radiation. Because this is going to sound funny. You know, one of the few objects in nature that is truly, truly black, that is really, really honestly black, there's one object in nature that is, it's 99.95% black. It absorbs almost everything. A star. A star is a black object. Can't be. They're bright. No, remember, black is not a color to us. Black is anything that absorbs all radiation that falls on it. Even if that object is hot and is emitting its own radiation, that doesn't matter. It's still a black object because any radiation that hits it is absorbed. So, for us, a black object doesn't necessarily look like that. Cold black objects would look like that, but not hot black objects. So, we like to study black bodies, and it's hard to move a star into the laboratory. So we've invented a curious kind of a black body. It can look like this. Imagine that I just take, I don't know, black iron plates and weld them together in this fashion. And, there's the red pen. So it's just black iron, rough surface inside it. And I leave just a small opening like this. That opening, if I send a ray of any kind of electromagnetic radiation, of course it's going to go in there, and even if it's likely to strike the wall and then reflect, it'll go up here. And it'll reflect again, it'll go over here. And it'll reflect again, and it'll go over here. And of course, this thing is going to keep reflecting around time and time again until it will very likely be absorbed. We're going to raise the probability that this incident ray is absorbed in the chamber by putting it in a darkened chamber, to reflect around and around and around inside. It's very likely, this hole is quite small, it's very unlikely that it will ever get back out the hole. It's going to keep reflecting in there until probability has it that it will be absorbed. That's how we manufacture a black object. And ladies and gentlemen, the black object is not the system, it's the hole. All the radiation that goes in that hole is absorbed. Therefore, it is a black object. None of the radiation goes in there and reflects back out again. For all intents and purposes, none of the radiation reflects back out again. So this is how we create an artificial black body in the laboratory, and it works pretty good, yes?
If we can see the light in there, doesn't that mean that some of the light is reflected back to us?
That means there is light being generated in there that is coming back out.
Right.
The radiation that you send in is absorbed, it heats the inside then generates new radiation. The radiation that's coming out is because of the heated interior, not reflected. Yeah, key word there, good question. Okay, absorbs all the radiation, it's a black body, instant light ray, accurate infrared. Now, what we would like to do is to take an object like this and raise its temperature, some high temperature T. Maybe we'll raise it up as high as 1200 kelvins, something like that. So the temperature is at 1200 kelvins. That's hot enough that we actually see it glowing. And just like she said, we'll see radiation coming out that hole, but that radiation will be generated because of the heat of the system, not reflected radiation. And we want to study the radiation that comes out. We'll talk more details about how we study the radiation when we get into the section on optics. Suffice it to say right now that the radiation is coming back out this hole, and this is radiation that is being generated from the surface here, the heated surface like that, and we're going to detect that radiation and study it. So for now, suffice it to say that I have some sort of a detector that converts the light signal into an electrical signal. We can measure how bright each individual wavelength is. And I'm going to plot it. Now that I'm able to do that somehow, like I said, I know I did not explain to you how we're going to do that. I will do that later. Just for the time being, just assume that we can do it somehow. And I would like to plot this for you. And most conveniently, we'll plot it like this. The vertical axis will be spectral energy density, which I'm going to write down E at nu d nu, like that. So I'll explain that in just a second. The horizontal axis like this is going to be frequency, which I'm going to use the Greek letter nu to be frequency, and of course that is proportional to 1 over the wavelength. So when we measure the wavelength over here, it allows us to determine what frequency is being produced, and then what we're doing is measuring how much energy is being produced at that particular frequency. So you find the frequency, how much energy you plotted. You find the next frequency, how much energy you plotted. So this is the energy within d nu of nu. So without whatever frequency plus or minus a d nu like that. And when you do that, you get an interesting plot. When you're done doing that, you get an interesting plot, which is definitely asymmetrical like that. What temperature were we at? That's at 1200 K. 1200 K. The shape of the curve is unique and asymmetrical. If we raise the temperature now, what was the next temperature? 1800. So if we raise the temperature now to 1800, T now equals 1800 K, and we redo the experiment, measuring the energy at each, and we discover that we have another curve, and I'm going to try to make this look significantly higher. The peak has moved, but mathematically it is an identically shaped curve. The curve has exactly the same mathematical shape. Things have changed. The curve